Okay, so it looks like we're going now. This, I'm hoping, is to be the first of a series on going through the Ethereum source code. So what I've got is a Google Cloud server that I've already uploaded all the source code to, or downloaded. And here you can see all the folders that are in the repository. A lot of these are just set up and how the directory gets compiled, and testing and stuff, and Dockers if you want to upload it to a server automatically. So I'm going to dive straight into probably the biggest, most known area of blockchain, being the blocks themselves. So in this is the core files, and under types is the one we're looking at here, block. So if we get into this file, you can see this package types contains the data types, the most important being the block. So Ethereum is very similar to the Bitcoin protocol in that they submit blocks to a blockchain, but that's probably where it ends. So instead of just sending a list of transactions, the Ethereum allows you to execute stuff. But the basic concept is that miners compile a block which has a list of transactions. In Bitcoin, the transactions are just money transfers. In Ethereum, they're actual source code that gets compiled. So, opening up the block source code, there is, right from the start, empty root hash, empty uncle hash. These are just helpers to, when you create stuff, you want empty, and because they're complex structures that aren't by default included in Go, they want to put them as like you can just call empty root hash or empty uncle's hash, and it'll give you something to put in there before you actually include any important information in it. Help us to create structures. CT euros. Here we have a block nonce. The nonce is what the miners increment or change to help them mine and change the SSH sum. So again, when you submit a block to the blockchain, the SHA the SHA is a hash, and if you do a hash over the block, it needs to be less than a number. That number is set by the difficulty, and it's essentially random. You have a block nonce of 1, and it'll give you a random SHA hash. If you have a block nonce of 2, it'll give you a completely different one. This can probably be seen with hash online calculator, maybe. If we go find one on the hash calculator, it says SHA-256, yeah, that's it. I know that the one in Ethereum is KKAK, which is an earlier version of SHA, like it was released before SHA-256. That's my understanding at least. Anyway, so you put hello, and it gives you a hash. And it's essentially random. This can be as many numbers, letters, characters as you want. It gives you a random result. Now, hello, exclamation mark, gives you a number that starts with 334. The difficulty says that you want this number here to be less than that. So all these first ones will have to be 0. And that's actually incredibly hard. And what the computer does is it increments the nonce. So you say 1, 2. And you can see they're not going anywhere quickly. It's rare enough that you'll get the B, so that's higher. 5. It's going nowhere. Like you want it to be 0, 0, 0, 0, 0, and it's super hard to do that. Anyway, so this character here gives you a 64-bit to work with. Encode the nonce. Takes a number, a uint64, and gives you a block nonce. So the best way to show this might be just in tmax cd core cd types vim block. Darcy's. So in this code I whipped up on the right, all I've done is included core types, which gives me access to everything in the types package here. So if I go encode, types dot encode nonce 22 0x equals print line didn't actually give me a full thing. Delete in that equals x. Go build, compiles, test. cd. So if I go into mine again, go into my test, and run the test. Let's clear it first. Vimgo and 64. Encode nonce 22, and then I'm printing it. So I'm calling this encode nonce, giving it the number 64. It's returning me a block nonce, which is just 8 bytes, 64 bits. And printing it gives me 64. If I do 22, clear in 10, gives me 16. Burp, that's not what I want at all. 64, clear. 100. Format print len. Use a package format without selector. Oh yeah. Where's that? So that's showing me that I've put the 22 there. So I'm not sure what it does when it prints. The next calculation returns a uint. That gives me my number back. Cool. So over here, encode nonce takes an integer, gives you a block nonce. Block nonce is just 64 bits in a byte, and it just sticks it in this like so. It really doesn't do anything too special with it. You got a 64-bit integer. It's put into 64 bytes. It's mostly so it's just structured in a way that can be appended onto a block very easily and can be changed very easily. This function here just returns what's in it straight away. So ideally, when you're running a miner, you are go run main. You are starting with a 1, then you're incrementing it with 2, and it puts 2 in it, and you're incrementing that until your hash here gets to a certain number. And a certain number means that this is in hex. A is higher than 10. 8 is 10, excuse me. A is higher than 9, 9 is higher than 8. But you want the first X amount to be 0 depending on the difficulty. The more people that are mining, the harder the difficulty. This is why at the start of the blockchain, the very first Bitcoin, Satoshi won so many, because he was the only one running it and the difficulty was so easy. He probably would have won anything. So you're incrementing this nonce, and all you're doing is giving the miner program some easy functions to put a number in there and to get it back. Underneath it, we have marshal text. Marshal text is something that Go uses a lot, and it's where they put a structure or something into a string that can be easily printed, or probably more likely put into a file. So this takes you to block nonce, gives you an array of bytes back, and it'll be a string with a 0x in front of it. So that literally just means that when you are printing stuff and saving it to a file or wherever you are, the database probably more likely, it's easy enough to find and to read about. So marshal text. Cool. So hex utility bytes of the whole thing marshal text. And that gives you a list of the bytes that have gone into it. I'm actually not too sure. Text Go lang. I'm not too sure why that's not 0000064. 02, whatever. Off chance that that is big endian or something encoding. Unmarshaled text takes it back the other way. So if you've got this, do it, X. You can get it back into a nonce. So in this case, let's try that actually. That's the same one. Encode nonce to marshal into the text. What's that say if it's a string then? String. Yeah, there we go. Okay. So that's a string of the letter 2. Number 2. 0x 0000000000002. And that makes more sense. ASCII chart. So show more. No, it's not. You lied to me. 64. Decimal hex. Character 0 is 48. 0, 120 is an X. 0x 00000000050, which is a 2. So that's all it's done. Puts it into a byte string. Now, unmarshaled text here takes it back out of it. So, if we have y equals block nonce, how do you do this in Go? New type Golang. New. Does that work? Looks like it will. Block nonce. Types of block nonce. Why is declared and not used? Hate that error. 0. There's no new variables on the left side of... Yeah, of course it is, because I'm not using that yet. Fine. Okay. Y equals... No, not equals. Unmarshaled text. X. In here, Y. And you're not printing anything. Why are you not printing anything? There you are, 2. So that's giving me the structure back. 0, 0, 0, 0, 0 with a 2 in it. So 2, we're taking the number 2, we're encoding it into a block nonce, and then straight away we're marshalling it. So it puts it into text in this X variable. New Y variable, unmarshalling. So we're doing the reverse now. We're taking a text string, and the text string has 0x just in ASCII, and then it puts it back into a block nonce. These are all mostly just helper functions, because when you program a miner, which is probably inbuilt into Go, definitely is inbuilt in Go, in Get, it needs to have these things to play around with it quickly, because you're trying to mine 1,000 kilohashes a second or something ridiculous. And you need to change that obviously 1,000 times a second. So here we now have the block header. This stores all the information that goes into a block. Excuse me one moment.